Hello everybody, in this lecture we will be solving 1976 IMO problem number 4. Here is a view of this problem. We would like to determine the greatest number who is the product of which is the product of some positive integers, and the sum of these numbers is 1976. Looks like this problem is pretty badly worded, but the main idea is this. So you have you would like to find a partition of 1976. So let's create one. For instance, let 1976 be equal to a sub 1 plus a sub 2 plus all the way up to, let's say, a sub n. So this is a partition of 1976, but in such that we would like to maximize the product of a sub i's, namely a sub 1, a sub 2, up to a sub n. So how can that be done? How can I split 1976 into pieces such that when I multiply the pieces together, I get the highest available product, highest product that I can get? Well, the idea is the following. So let's focus on first on the AI's. So let's assume that there exists let a sub j. So you start by splitting 1976 any way you want. So you partition it as you want, and we are given this partition. And then I do the following. If I realize that if any of the pieces is greater than or equal to 4, then I claim that I can split that piece, whichever that piece is, into two numbers in the following way. Into the numbers 2, so let's write that down. Then split a sub j into 2 plus a sub j minus 2. And I claim that, well, this number is obviously equal to a sub j. I claim that the new partition, the product, is greater than a sub j. So therefore, let's have a look at the product. Notice that 2 times a sub j minus 2, which is 2a sub j minus 4. This is definitely greater than a sub j, because we can split this as a sub j plus a sub j minus 4. And notice that this expression is greater than or equal to 0, right? Because of the given condition, suggesting that this thing is greater than a sub j. So therefore it pays off, it makes sense to split a sub j into pieces, smaller pieces, one of which is a 2 and the other piece is reduced. And as long as that piece is greater than or equal to 4, keep splitting. So in each split we increase the counts of 2's. And depending on if a sub j is odd or even, this process will eventually stop when a sub j, the new number obtained, becomes a 2 or a 3. So we will have eventually, so this continue this process until a sub j is less than 4. Eventually we'll have we will have a bunch of 2's and maybe a 3, depending if a sub j is odd or even, right? So if it's odd, then we will get a 3 for sure. But then repeat this process for each a sub j greater than or equal to 4, right? And this way we guarantee that, implying that we'll have, this time we'll have 2's and 3's now, right? Possibly many more 2's than 3's. But then how about the numbers which are less than 2 or 3? Right, so we understand that this procedure makes sense. It optimizes the product, right? So look at this product. The product exceeds its previous number, right? So the previous product, right? So what if we started with some 1? So what if initially in the initial partition there used to be a couple of 1s, right? What if a sub I was equal to 1 initially? What would you think? Of course, you would simply add that 1 into one of the other parts and eliminate this one, right? Add 1 to any of the other parts, and then go back to this step and then apply the process of splitting them into 2s and so on, right? So eventually, right, so because when we add 1 to one of the other numbers, the list of which is 2 or 3, right, even if our number, so if our number is a 2, for instance, if you add 1 to a 2, you get a 3, which I claim is good enough. If our number is a 3 or higher, we'll get a 4 or higher, and we split. The splitting business is very efficient. It maximizes the product, as we have seen here. The product after splitting is greater than, at least for that term, is greater than for that term. And if we apply this process to all the terms, obviously the overall product will be greater than the previous product. So therefore, after we apply all these steps, it implies that our product will become 2 to the power x times 3 to the power y. But shall we stop there? Not really. Let's see which one is more efficient, the 2s or the 3s. So it depends. So if x is greater than or equal to 3, namely we have 3 or more 2s at the final situation, which is very likely going to be the case, then we just observe that, then notice that 2 times 2 times 2 is of course, let me write it this way. Then 2 plus 2 plus 2 is obviously 3 plus 3. In terms of their sum, they are equal. However, 2 times 2 times 2, which is equal to 8, is less than 9, which is 3 times 3. So therefore, the 3s are more efficient than the 2s. So it makes more sense to split each of the 2s. For instance, if you have 3 2s, just split them such that, so combine them and then split them so that you have 2 3s instead. So finally, this product will eventually reduce to the following. So the product will be increased to the following: 2 to the power a times 3 to the power b, where there's no more 3 2's in it, right? Where a is either 0 or 1 or 2. Now let's see the situation for 1976. It turns out if you divide 1976 by 3, you get 3 times 658 plus 2. So, and I claim that this is the best way to partition it. So as a result, this would imply that the optimal product, the maximal product, is equal to 2 times, a single 2 times 3 raised to the power 658, and this is greater than any other product that can be done, that can result as a result of this partitioning business. And that solves our problem. Hope to see you guys in our next video.